Welcome to the second part of VCAA Specialist Math 2021 exam papers. In this video, we will present exam paper 1 questions 5 to 8. Question 5 was well answered. However, the common problem in question 5 is that students did not differentiate the constant term to get 0, as well as incorrectly substituted the coordinates. In question 6, some students failed to conclude correctly for linear independence, even though they were able to find the p-values for linear dependence. In part A of question 7, some sign errors were made when the trigonometry function was integrated, while in part B, most students did not attempt or unable to give the correct times at which the maximum occurred. Most students did well in part A of question 8. In part B of question 8, algebra errors were quite common in attempts to solve the resulting equations. Some students confused with the complex conjugate with the reciprocal. While it is possible to solve the equation beginning with the polar form, few students took this approach, and those who did rarely made any significant progress.
Hello, Math Champions! I'm Dr. Chen. If you want to improve your math skills and understanding so that you gain confidence, enjoy math more, and get better results, click subscribe and hit the notification button so that you don't miss anything.
Welcome to this VCAA Specialist Math exam paper series. In this video, we will present exam 1 questions 5 to 8 2021 paper. Let's start from question 5, which requires finding the gradient of the curve with the equation e to the x multiplies e to the 2y plus e to the 4y squared equals 2e to the 4th at the point 2, 1. To find the gradient at a given point, we need to apply the technique of implicit differentiation on the given equation. So we differentiate every term of the equation with respect to x. As it can be seen, the differentiation of e to the x multiplies e to the 2y with respect to e to the x, plus the differentiation of e to the 4y squared with respect to x equals the differentiation of 2e to the 4th with respect to x. Hence, the left side of the equation equals e to the x multiplies e to the 2y plus e to the x multiplies the differentiation of e to the 2y plus the differentiation of 4y squared multiplies e to the 4y squared, which equals e to the x multiplies e to the 2y plus 2e to the x multiplies e to the 2y multiplies y prime plus 8y multiplies e to the 4y squared multiplies y prime, which equals 0. Hence, after being further simplified, y prime equals negative e to the x multiplies e to the 2y over the sum of 2e to the square multiplies e to the 2y plus 8y multiplies e to the 4y squared. Then the coordinates 2, 1 are substituted into the y prime expression. So the gradient at the point 2, 1 equals negative e squared multiplies e squared over the sum of 2e squared multiplies e squared plus 8e to the 4th, which equals negative 1 over 10. In question 6, 3 vectors are given. Vector A equals negative I plus 6j minus 3k. Vector B equals 2i minus 8j plus 5k. And vector C equals 3i plus 2j plus modulus of 1 minus p squared k, where p is a real constant. The question is to find the values of p for which the 3 vectors are linearly independent. As we have already learned, if vectors A, B, and C are linearly independent, then there are no coefficients alpha and beta exist to satisfy the relation vector C equals alpha multiplies vector A plus beta multiplies vector B. In order to find the values of P, we assume that the vectors A, B, and C are linearly dependent, and based on such an assumption, what we find are the values of not P. Therefore, we have vector equation of 3i plus 2j plus modulus of 1 minus not P squared, k, equals alpha multiplies negative I plus 6j minus 3k, or in parentheses, plus beta multiplies 2i minus 8j plus 5k, or in parentheses. After equating all the components of I, j, and k, we have three simultaneous equations. Negative alpha plus 2 beta equals 3. 6 alpha minus 8 beta equals 2. And negative alpha plus 5 beta equals modulus of 1 minus not P squared. Solving the first two equations, we obtain alpha equals 7 and beta equals 5. Here we continue to work on question 6. Based on the calculated values of alpha and beta, and according to the third equation, modulus of 1 minus not P squared equals negative alpha plus 5 beta, which equals 4. So the values of not P equals plus or minus square root of 5. That makes vectors A, B, and C are linearly dependent. Hence, to make vectors A, B, and C are linearly independent, P can be any of real numbers except negative square root 5 or square root 5. In question 7, the velocity of a particle satisfies the differential equation dx over dt equals x sine t, where x centimeters is the displacement relative to a fixed point O at time t seconds. Initially, the displacement of the particle is 1 centimeter. There are two parts in this question. Part A is to find an expression for x in terms of t. Part B is to find the maximum displacement of the particle and the times at which this occurs. Here we continue to work on question 7. In part A, since dx over dt equals x sine t, the variables x and t can be separated in this case. So dx over x equals sine t dt. We integrate both sides of the equation and obtain logarithm base e of modulus x equals negative cosine t plus a constant c1, which gives x equals a multiplies e to the negative cosine t, where a is a constant yet to be determined. According to the given criterion, x of 0 equals 1 centimeter, which means the initial displacement is 1 centimeter. That gives a equals e. Hence, x of t equals e multiplies e to the negative cosine t, which equals e to the result of 1 minus cosine t. As for part B, since 1 minus cosine t is periodic, obviously when cosine t equals negative 1, x of t reaches its maximum, which equals e squared. Hence, when t equals 2k plus 1, where k is an integer, cosine t equals negative 1, the maximum displacement equals e squared. Question 8 consists of two parts. Part A is to solve the quadratic equation z squared plus 2z plus 2 equals 0, where z is a complex number. Part B is to solve another quadratic equation, z squared plus 2 times the conjugate of z plus 2 equals 0, where z is also a complex number. Now we start to solve the equation in part A. Since the quadratic equation z squared plus 2z plus 2 equals 0 can be written to z plus 1, or in parentheses squared minus I squared equals 0. it can be factorized to z plus 1 plus I, or in parentheses, times z plus 1 minus I, or in parentheses, equals 0. Hence, z1 equals negative 1 minus I, z2 equals negative 1 plus I. Alternatively, we may directly apply the quadratic formula to solve this equation. In this case, here A equals 1, B equals 2, and C equals 2. So z equals negative 2 plus or minus square root of the results of 2 squared minus 4 times 1 times 2, all over 2, which equals negative 1 plus or minus I. Hence, accordingly, z1 equals negative 1 minus I, and z2 equals negative 1 plus I. As for part B, we assume that y equals x plus yi, which relates to the conjugate of z equals x minus yi. Since z squared plus 2 times the conjugate of z plus 2 can be written to x plus yi, or in parentheses squared, plus 2 times x minus yi, or in parentheses plus 2. The equation is transformed to x squared minus y squared plus 2x plus 2, or in parentheses, plus 2xy minus 2y, or in parentheses I, equals 0. Then we equate both of the real and imaginary components to 0. So we have two simultaneous equations, x squared minus y squared plus 2x plus 2 equals 0, and 2xy minus 2y equals 0. The second equation is factorized to 2y times x minus 1, or in parentheses equals 0, which gives x equals 1. After the calculated x value being substituted into the first equation, y values are obtained, which equals plus or minus square root 5. Hence, z1 equals 1 plus square root 5i, z2 equals 1 minus square root 5i.
If you enjoyed this video, please give it a thumbs up and subscribe to help me make more math content like this. I will see you in the next video.